Closely related to the ratio test is what's called the root test. And the reason I say closely related is that underneath the surface, they're both based on a comparison, a direct comparison to a geometric. So the first thing that might jump out at you here is that the conclusions are exactly the same. They're still a row. Same conclusions based on row. But the limit you take is different. It's the limit of the nth root of your terms, not a ratio of terms. And slightly less restricted. Remember, for ratio, we needed strictly positive terms. Here, they can be 0. You can have terms that are 0, but you just can't have negative. Okay. So let's go ahead and look at the first one. And again, it's going to be a similar argument. I'm going to try and create a geometric that is larger than this, or eventually, but is convergent, so we can do a direct comparison. So if we look at number 1, let's say that the limit as n goes to infinity of the nth root of our terms. So this means the root is going up as well. So the nth root of our terms equals some row, which is less than 1. Again, I can find an r because the continuity of the real numbers, there's always numbers in between on equal numbers. So let's make r be bigger than rho, but still less than 1. And so if that limit's headed to rho, just like my argument on the ratio test, it eventually has to be less than r, because it's getting closer and closer and closer to rho. Rho is less than r. So at some point, eventually, or for all n bigger than big N, the nth root of my terms is less than r. Well, now just raise both sides of that statement to the nth power. So that means all of my terms then at that point are less than r to the n. And r is a number less than 1. So at least from n to infinity here, we've got a convergent geometric, right? Absolute value of r is less than 1. So what do we have? We have terms that are, first of all, by the presupposition, they have to be non-negative. So, but they're bounded above, at least eventually, they're bounded above by this geometric, which is convergent. So at least from big N to infinity, our series converges by dct. And it never hurts to put finitely many terms back in. Once we know this is convergent, adding in n terms, finite number of terms, won't change the convergence or divergence thereof. Whoops. We want to switch this, right? It's supposed to be starting at, say, 1 of our a sub n's converges. And on the flip side, exact same argument. Just change the direction of all these inequalities, and then you've got a divergent geometric that we're bigger than, and we diverge. Number 3, just like on the ratio test, I won't go through it again, but if you do a p-series, convergent p-series will give you a row of 1. Divergent p-series will give you a row of 1. So a row of 1 is inconclusive because you can have both convergent or divergent series. One thing to note, because of the close connection here, if you get something inconclusive on root test, it's going to be inconclusive on ratio test. So if this fails, if you're doing a root test and you get rho equal 1, don't try ratio test next because you're going to get a rho of 1 again. So, and again, because p-series will generate rows of 1, if I get a row of 1, I typically will next think, should I really be doing a LCT or DCT with some p-series? So a row of 1 is an indicator that you might be dealing with something that's comparable to a p-series, so LCT or DCT at that point. So next, we'll look at an example of using the root test.